Now let's look at arc length for parametric equations. So there's a lot here too, so pause and copy as you go. So if a curve C is given by the parametric, this was looking at before it's defined parametrically. So this is how arc length is defined, how arc length is defined with a explicit function of x, so y equals f of x, like this. Okay, then this is what is given. And we've done this before. We did this in the past. I forget exactly when we did it, but either derived it or gave it to you. So you get, so the length from one, so you'd like to take a parabola, right? And you integrate from A to B, then this is the length. So you have to take the derivative and square it, and then add 1 in the root, right? So it can get kind of messy, but that's how you did it. Okay, so parametrically, let's suppose C is a smooth curve, and it's simple, does not cross itself. It's stated out here somewhere. Given by f of t and y equals g of t for t between A and B. Okay, also, I already said that, it does not cross itself. So it's a simple curve. Not closed necessarily, of course, but just simple. All right, so then consider a partition of AB given by this should look familiar, and let delta t sub k be t sub k minus 1. Okay, so that's the difference of the larger value and the smaller value. And let p sub k be the point defined by the parametric equation. So it's f of t sub k, g of t sub k. Okay, and then we're going to say, or have, if d of p sub k minus 1 to p sub k, so it's like from here to here on the graph, is the length of the line segment from pk to pk minus 1 to pk, then the length of the broken line, so now we're looking at this broken line like this, you're adding those all up. So d is this distance of each one of those. Okay, so you're adding those up, that's L sub p, is that sum, that's the length. All right, then we, as before, we're gonna say the norm of p, so p is this partition, that's the partition. The norm of p is the length of the largest sub-interval. So whichever interval is the largest, that's the norm, just like we had. And so we're going to define the length of the curve, of this smooth curve like this. We're going to define that length to be the limit of the L sub p's of that as the norm approaches 0. Okay. And call L the length of C from P naught to Pn. So just like we said, so this is C. C is my curve. Okay, so just thought I'd throw out here, formally you would say it like this. If for every epsilon, so for all epsilon, there exists a delta greater than 0, such that the norm of P less than delta for every partition P implies the absolute value of L sub P minus L is less than epsilon. So this is basically as close as you want, because that's arbitrary, by making delta small enough. Okay, and then that's basically, it's making that the norm of P, the distance small enough, the length of the largest segment small enough. Okay, so D, for calculate from P naught or P sub K to K minus 1 to K. So this distance, we use the distance formula between those 2 points. So it's the function values, but now they're defined in terms of f and g, not like x and y. So this is what you get for the distance formula. So if you take any point, you have x comma y, and then you take the difference of the x values, difference of the y values. That's what this is doing here. And you square it. Now, we're going to use the mean value theorem. So the mean value theorem I wrote over here is this concept. You basically have a secant line and you have a tangent line. There exists a c, so in the interval, such that f prime of c is equal to that slope. So you have this slope like this, right, is the same as some c value between those two values. So we have an interval that is t sub k to t, well, reverse that. T sub k minus 1 to t sub k is the interval. So there has to exist a value within that interval, we're going to call it w sub k and z sub k, such that, and then you basically use this form here, that f of t sub k minus f of t sub k minus 1 is equal to f prime of the w sub k, and then that's the interval. That's like your b minus a, right? That's like that. But it's just, that is delta t sub k. Okay, so there's a lot going on here. Pause that and read through that again. Okay, z sub k is in here, right? So here's your mean value theorem statement. So what that allows us to do is replace this difference with f prime and g prime, delta t sub k. Okay, so when you simplify that and substitute in, you get those primes, and then the delta t sub k can factor out. And it's positive, so no absolute values. Okay, so then you take the limit as the norm of the partition approaches 0. So it's the Riemann sum of this delta t sub k, so that's your dt. And then you get this formula. Okay, again, a lot going on there. Spend some time copying and reading through that to try and understand it, where I'm getting all those little details. Okay, let's this next question, try on your own. It's pretty much just finding the derivatives and plugging into the formula and simplifying. I have the solutions here, the whole thing, if you want to try it. Okay, so try this on your own first, and then you can look through stuff. Okay, last thing is surface area, surface of revolution. So I'm not going to go through the derivation of this. This, I'll zoom in on this again if you want to actually go through it, similar to how I've done it in the past. This is the derivation they do in a different book. Our book doesn't really go through it much, so that's why I threw that in there. Okay, so let's go through the theorem. All right, so let's so if C is smooth, given by a x equal to f of t, y equal to g of t, and does not cross itself, so it's simple. T between A and B, then the surface of revolution S is given by this or this. So one is revolving around the x-axis, one is revolving around the y-axis. Okay, so we can use that to evaluate surface of revolution for parametric. Okay, so take a look at that, kind of study a little bit. So this is your y value, this is your x value. Both have to be positive. Okay, and then if you want to look at how that's derived, you can pause that and look through that more carefully. I'm not going to go through the whole thing. But you can see the strips that you're revolving, and you have like little segment there, and then that strip's revolved. So you end up with a distance, and you revolve it. That's the kind of stuff we're doing. Okay. Let's look at this example. I like these questions. I don't know why. Verify that the surface area of a sphere of radius A is given by this. It's basically verifying formulas that you may have remembered or seen before using calculus now. So you can test it and see that you know that the surface area of a sphere, if you looked it up, maybe, is 4 pi r squared or 4 pi a squared if it's a radius a. So you have a sphere, right? Let's see if I can make a decent sphere. So what's the surface area of this sphere? That's the question. So surface area, you can basically take a circle like this, take this circle, and then revolve it around the x-axis. So that's how we're going to define it. We define it parametrically and then substitute into the function. So try this again on your own, and you know what you should get. You should get 4 pi a squared when you're finished with that. Okay, so this little recap, basically know how to apply the formula, arc length. I want you to study this concept. You don't have to like reproduce it, of course, but I just want you to know how things are derived. All right, so you need to know how that's done. Might be something to do in the final, but just for your own sake, I want you to do it. Let's see, back in here. So second derivative, you'll just apply these formulas. And then first derivative, know how to do those. You'll find slope of the tangent line, that kind of thing. Okay. One more section to go. Well, we got to define, we're going to go into polar coordinates, and then graphs of polars, and then that's it.